Hi viewers, this is Sri Ramlu. So before watching this video, please subscribe it. Bridge rectifier. The bridge rectifier is a full wave rectifier. It consists of 4 diodes connected as shown in figure. So it is like a full wave rectifiers. Whatever things present in the full wave, the same thing will present here, but the difference is in diagram only, construction only. Their mathematical part is the same as that of the full wave rectifier. Okay, and the secondary terminal of transformer S1 and S2 are connected to the junction F and H. Here the secondary terminals are connected. Secondary terminals, there are the 2 terminals for the transformer. So here you see the transformer. This is the transformer, right? And this side coils are called primary and these are called secondary. So this is primary coils and these are the secondary coils. And the secondary coils, this side is a S1 and this side is S2. And S1 is connected to what? It is connected to F and S2 is connected to H. Okay, F and H. Next. Right, and next one is the junction G and E are connected to the output across the load resistor. Okay, S1 S2 are connected to F and H. Okay, and G and E are connected to output where across load resistor, that is RL. See here diagram. So here it is a load resistor. So S1 is connected here, F, S2 is connected to H, but E and G are both are connected to what? To load. At a load only we take output. Next, an AC voltage is applied through the transformer during the positive half cycle. Here AC voltage means it is like in this form. Okay, so when it is like a waveform, so this is called positive half cycle, it is called negative half cycle. Okay, so AC voltage is applied across the transformer during the positive half cycle of AC input. Secondary terminals of the transformer S1 will be positive and S2 will be negative. Okay, so S1 becomes positive, right, and S2 become negative. See, so let me come across this. So during positive half cycle only. So during positive half cycle, so when the positive half cycle comes, so it become positive and this become negative. And this S1 is connected to what? It is across F. So here F you have, it is F. And F is connected here to D1 diode and as well as D2 diode, and S2 is connected to H, and H is again connected to two diodes, one is a D3 and a D4. Okay, now the diodes D2 and D4 conducts in forward bias, D1 and D3 are in reverse bias. Here D2 and D4 are forward bias and D1 and D3 are reverse bias. How? See here. So here positive, it is positive. It is positive means F is also positive. So S2 is negative means H is also negative. So it is you know the diode. It is a diode when it is like this, and this side is P type and this side is N type. That is we know well. And when it is a positive, see here this positive is connected to P side to diode D2 and N side to the diode D1. So it is a positive, and for the diode D2 this side is also positive. So that is why positive it become forward bias. That is the reason. And next come to the D1, and this is a positive connected to the negative. So when it is a positive connected to the negative, then it becomes reverse bias. Okay, that is why D1 is reverse biased. Now let me cross the S2. So it is negative H point. H point is connected to D4 and D3, and for D3 it is negative, and this side is a positive. So positive negative, it becomes reverse bias, and this side is negative and is also negative. Negative negative, it becomes forward bias. Okay, so that is why when S1 is positive, S2 is negative, then diode D2 and D4 are the forward bias, and these two are reverse bias. Means current do not flow this side. Only current how does flow? So this current comes like this and through D2 and come across this side, and now from this side. So it is like this, current flows in this direction. Okay, and appear across RL. So that is the direction. So this side is direction is this one, and this side direction is like this. Okay friends, next let me explain with the negative. Under this condition, the direction of the current flows through the RL will be in downward direction. Okay, so when D2 is a forward bias, D2 and D3 is forward bias, and these two are reverse bias, then current flows. Next, during the negative half cycle of input voltage, the secondary terminals of transformer S1 negative, S2 positive. Now it is reverse. Okay, now S1 is negative and S2 is positive. Then what happens? The diode D1 and D3 in forward bias and conducts, and the diode D2 and D4 are will be in reverse bias. Okay, here now in during the when during the negative half cycle, S1 is negative, S2 is positive. In this side, in this case, these two are forward bias and these two are in reverse bias. Okay, let me come across diagram. Now it is negative, this is positive, and negative is also come here, and it is negative is dividing these two side, and this side is a positive side to the diode D2. So it is a positive side, means it is P type. So P type is connected to the negative, means a negative positive become it is a reverse bias, and negative comes this side also, and already this side is negative. This negative and negative, it is a forward bias. Okay, now it is a positive. So here also positive. Positive is connected to this side and this side also, and this side is P type and N type. So P type positive, P type it conducts, and it is positive, and this side is negative. Negative positive, it is reverse bias. So that is why these two diodes, okay, these two diodes do not conduct, but this and this conducts. Then the direction of the current flow, see here. So current comes like this and flows in this direction now, and comes like this in this direction, and from this side current how does flow? Current flows like this, see here the directions of current like this, and from this side this. Okay, so both are again meeting at across load RL. So at RL we can take output, right? So this is the explanation of the diagram. Now, even now the current flows through RL will be in downward direction. In both cases it is in downward direction. Okay, here and here, both cases. So the current through RL is in the same direction in both cycles. So in both cycles current is flowing. Okay, so that is why the waveform will be like this. See the waveform. Suppose it is AC voltage, it is input voltage. When it is a positive, when it is a positive half cycle, then we know that S1 is positive and S2 is negative. Then which diode conducts? D2 and D4 diodes conducts. So it is because of D2 and D4. And next, during the negative half cycle, it is negative, it is positive. S2 is positive. S1 is negative, S2 is positive. And during that, then D1 and D3 conducts. When D1, D3 conducts, then this waveform will get output. So like this, for positive side, for positive on this, and for negative on this, positive on this. So like this we get continuously one side waveform. So one side waveform is simply DC only. It is not pure DC, but it contains some pulsating DC. And now mathematics, that is analysis. Let the input voltage Vi is equals to Vm sin omega t. So input voltage can be represented like this. Why? Because it is a sinusoidal, it is a AC voltage. The current through the diode D2 and D4, load resistor RL, through the load resistor RL, S1 is positive and S2 is negative. Yes. So during this what happens, the positive half cycle only we are sending. Positive half cycle means that is 0 to pi only. Negative half cycle is pi to 2 pi. Okay friends, keep in mind, positive is 0 to pi, negative is pi to 2 pi. So during the negative half cycle, diode D2 and D4 do not work. So that is why it is a negative half cycle, it do not work, current cannot flow. Okay, so during the positive half cycle, it is positive half cycle, then current flow, that current is I1 is equals to Im sin omega t. And here Im means what? Im is Vm by RL plus Rf, where Rf is a diode resistance. Similarly, current through the diode D1 and D3 resistor RL, okay, S2 is positive now, S1 is negative. So it is now, the waveform is like this. Okay, during the negative half cycle. During the negative half cycle, we know these two works and these two do not works. That means this current and during half cycle, so positive half cycle, there is no positive half cycle, only negative half cycle. So pi to 2 pi, so only pi to 2 pi conducts and this cannot conduct. Why? Because we are not giving any positive half cycle, negative half cycle only giving. So that is why the current is I2 is equals to Im sin omega t. So I1 and I2 if you add, then you can get the total current I. The total current through the load resistance RL is the sum of the two currents I1 and I2 is this one only. So now we have to calculate the DC output current and output average current or output voltage, everything we have to calculate. So what we have calculated in a full wave rectifier, the same thing here we have to calculate, the same everything is same. Alright. So average current can be calculated like this, right? So average current, we know how we calculate, already explained in full wave rectifiers. So generally average means in mathematics we write according to integration only. So 0 to 2 pi, it is a full wave d omega t by integration 0 to 2 pi just d omega t. In denominator you do not keep anything here, but in numerator you must keep I, then only it is called average current. If you want to calculate average voltage, substitute here V and don't substitute here anything. Okay, so integration 0 to 2 pi, its value we know, that is how we get according to mathematics 2 pi we get. Okay, but we do not get. Why? Because R value is here, I value is here. So take I value and substitute in this at this point from equation 1 and 2 only. So 0 to pi, so what I said just now, so like this only we have to calculate here. So IDC is equals to 0 to 2 pi I into d omega t. So we are differentiating it, not a t, not omega t. So we are integrating it d omega t only, not omega, not t. So by combining omega t, right? And here I am separating. So for the two cycles, 0 to pi is a positive half cycle and pi to 2 pi is a negative half cycle. So that is what is kept, it is negative. Okay friends, why it is negative? Why it is two parts? It is 0 to pi is a positive half cycle and pi to 2 pi is negative half cycle. And during the positive half cycle, the I1 current flows, and during the negative half cycle, I2 current flows. Already we have discussed above. So see here, during the positive half cycle, I1 current, and during the negative half cycle, I2 current. So negative is pi to 2 pi, positive is 0 to pi. Now substitute the values I1 and I2. So I1 is this one, I2 is this one, and take outside the common factor. Just now I told you the denominator how we calculated. So take outside the Im and by 2 pi. So Im by 2 pi, it is taken common, and it is a 0 to pi sin omega t d omega t minus of pi to 2 pi sin omega t d omega t. So their integration we know, integration of the sine is minus cos, integration of sine is minus cos, but limits are different. their limits are different. So here the limit is 0 to pi, here limit is pi to 2 pi. Substitute first 0 to pi in this equation and pi to pi in this equation by doing minus. But before that, what we have to calculate, we have to take outside minus, this minus, take outside. If you take these two minus outside, then here minus, and we are not taking outside this minus, so that is why this minus as it is. Okay, and now substitute the values. If you substitute this pi and 0 values, then you can get like this, and this is you get like this. Cos pi we know minus 1, but cos 0 is 1 only. Cos 2 pi is a plus 1. Cos pi is minus 1, minus minus it become plus, right? And now minus 1 minus 1 minus 2 plus 1 2, and it is minus 2. So minus 2 minus 4 minus plus 2 ones are 2 twos are. So that is why IDC is how much? That is 2 Im by pi. Similarly, VDC we have to calculate. So VDC can be calculated by using the Ohm's law. Voltage is equals to current into resistance. Okay, so same thing is applied here. Voltage is if you take the DC current, then DC voltage we get. AC current, AC voltage you get. But here we are calculating DC only. So that is why VDC is equals to IDC into RL. RL, why we have to take RL is resistance, load resistor that is present across at output only. So at output we take DC only. So that is why we have to write RL, and we do not write RF. RF indicates AC. Okay, and take a IDC value here and substitute at this point. Then this is, and we know the Im value just I told you about. So Vm by Rf plus RL. So this is, from this take outside the RL common. Yes, RL is taken outside common. RL cancel. Then it becomes Vm by 2 Vm by pi into Rf by RL plus 1. So if RF is very much greater, RL is very much greater than the RF, then this term can be neglected, means its value is approximately equal to 0. So then what happens? We get 2 Vm by pi. And now RMS current. RMS current means it is a AC current, pulsating current. Pulsating current is also called as RMS current, or pulsating voltage is also called as RMS voltage. RMS means root mean square. Okay, so first take root. So root is taken. Okay, whole power 1 by 2 means it is root. Mean, so just above what we have done, that is integration 0 to 2 pi I d omega t by 0 to 2 pi d omega t, just now I told you about. That is a mean value, and square it to the mean value, so it is squared. So to the I value only squared, only I value we have to square. We do not square whole, only I square we have to do, only for the I current only we have to square. So that is why here I square, here also I square. Okay friends, that is a root mean square, right? So this term we know that is a 2 pi, so it comes directly. Next Im, here Im, but square is there, so outside if we bring outside it become Im square. So yes, our m square by 2 pi is taken outside, and sin square, here also sin square remains same. Here the limits and limits are different. Next, and here sin square can be written as 1 minus cos 2 omega t by 2. So there is a general formula, and it is a very basic formula. 1 minus cos 2 theta can be written as 2 sin square theta by 2, or 1 minus cos 2 theta by 2 is also written as a sin square theta. Now above sin square theta is given in this form is given, and we have to write in this form 1 minus cos 2 theta by 2 we have to write. So that is why 1 minus cos 2 omega t by 2 is written. Okay, now this 2 also take outside. Yes, taken. Then it becomes like this only. Next, okay, 2 2 is 4, here it becomes, we know, so just now see above, here 2 into 2 it becomes 4. Next, and integration, apply integration inside. So to the what inside is applied, see the from above diagram. So integration is applied to all the individuals, so it is applied to this one and applied to this one also. This integration applied to one and as well as cos 2 omega t only, so that is why we write like this. Okay, and we know the one integration according to d omega t, so it is d omega t, and here cos 2 omega t integration is sin 2 omega t by 2. Okay, next its value is the same thing, and its value is also sin 2 omega 2 and sin 2 omega t by 2. Okay, and its limit is 0 to pi, its limit is pi to 2 pi, and we should not forget the root value. Okay, we continue it till the end, and now substitute the limits values here. Here also substitute the limits in all the 4 points in the 4 equations. Substitute the limits values. First pi value and next 0 value, next here also pi value and next 0 value, and next here also, here 2 pi, next to pi, and here 2 pi, right? Already 2 pi, already 2 omega t is 2 into 2, it becomes 4. Next pi, so like this, and we know that what you know, its value as it is, but sin 2 pi becomes 0, sin 0 0. Here it is the difference is pi only, and at 2 2 ja 4 pi becomes 0, sin 2 pi is also 0. Now here 0 0 0, it is a plus pi, it becomes 2, power 1 by 2 is as it is copied, and here 2 1s are 2 2s are, so that is why here 2 value we get, and pi is also get cancelled. Then final value is by allowing the root value, it root for square cancelled, so im by 2 is there, it becomes root 2. Okay, so like this it is a IRMS value. So if you know the IRMS, VRMS can be calculated easily according to Ohm's law. Just now I told you, voltage is equals to current into resistance. So current is, if it is RMS current, voltage is also RMS. So RMS value we know, just now we calculated above, that value is Im by root 2 into RL, and Im value we know, that is Vm by 2 Rf plus RL. Substitute value here, so it is as it is, and take out RL value. So if you take outside RL value, this RL that RL get cancelled, we get this one, and apply this condition, then this term is 0. Then here root 2 into 1 becomes root 2 only, so that is why Vm by root 2. So like this we have calculated voltage, DC voltage and DC current, AC voltage and AC current, that is RMS current. Okay, now power we have to calculate by taking the above formula. Power can be calculated. Power formula is that power rectifier efficiency it is, and it is defined as the ratio of DC output power to AC input power. It is called efficiency, and it is denoted by what? Eta. Okay, efficiency is output DC power by input AC power. Okay, we have to calculate PDC and PAC separately, and then we have to substitute in this equation, then we can get eta value. Now power can be written as current square into resistor. If it is current is suppose a DC current, then take resistor is RL, and it becomes PDC. Okay, so we know the IDC, so same thing, IDC value just now we have calculated, that is the 2Im by pi, and it becomes whole square into RL. Now so if you apply the pi square value, it is square apply 4, it is I square pi square, right, into RL. And next AC. So AC can be written as, AC is also same thing, power is equals to I square into RL, but we do not take here RL. Why? Because of AC not only present at the output and also present at input. Okay, so that is why RL plus RF we have to take, so that is why here RL plus RF is taken, that is the reason. And I square RMS is RMS value we know, that is Im by root 2 whole square. For square it is square, and it get root cancelled, so then it becomes like this. Okay, and their ratio is eta value. Now substitute the PDC and PAC formula. So if you substitute, then we get like this. And now from this equation, So Im square cancel, right? And next this 2 goes upside, and 2 into 4 it becomes 8, and here the pi square is there, so written as pi square as it is, and the remaining terms are same. And here also what we have taken common, here RL is also taken common. If you take RL cancel. Okay, so then this is the formula. Okay, we know that is how does it they have come. And you know the 8 by pi square value is 0.812. So 0.812 is written, and in terms of percentage it is written 81.2 percentage. So this is the eta value. Eta value is 81.2 percentage pi 1 plus RF by RL. If you apply the condition RL is very much greater than the RF, then what you get? You can get that is 81.2 percentage only. Okay, then why? Because it becomes 0. Okay, then 81.2 percentage you get. Next, ripple factor. Ripples means AC. The ratio of ripple voltage to DC voltage is called ripple factors. The ratio of ripple voltage is also called as RMS voltage or RMS component to DC component is called ripple factor, and it is denoted by gamma. So gamma is equals to ripple voltage by DC voltage. So by solving this we get directly this one only, IRMS by IDC whole square minus 1. So we know already IRMS and IDC values we have calculated. IRMS as Im by root 2, IDC is 2 Im by pi we got. So here Im gets cancelled. Okay, now after cancelling them we get this equation, this one, and next if you apply this square to then it is a pi square by 8. So already we have I told you 8 by pi square as a 0.812. So their ratio is big ratio, and if you simplify, if you solve this one, you can get like this. So gamma value is 0.48 means at output less AC present comparing to the half wave rectifier ripple factor is 1.21, but here value is again reduced, means at output AC is reduced. Okay, so in full wave rectifier and bridge rectifier AC will be reduced comparing to the half wave rectifiers. Okay friends, don't forget this video watching till the end and subscribing, and share it to your friends also if they don't know. Thank you friends.